Welcome back, class. So today I want to pick off where we left off last time when we discussed all of the geometries. And I want to talk about one other kind of compound with geometry and then get into talking about polarity of molecules. So we talked last time about normal structures that we've looked at that have one central atom and are surrounded by, some other number of atoms and or lone pairs. But what if we have larger type organic type molecules that have multiple central atoms, right? So if we have something like glycine here, right, you could see that we have 4 central atoms. So how do we come up with a geometry for a molecule like this? Well, under our Vesper theory idea, we would in essence have a geometry for every central atom. So in other words, each central atom would have its own unique geometry or its own individual geometry, looking at the shape around it. So we kind of isolate each of the central atoms and assign it a geometry. So, for example, if we look at the nitrogen, we see that it has 4 electron groups, 3 bonds, 1 angle, 1 lone pair, which means it's part of the tetrahedral family, but the molecular geometry is trigonal pyramid. Right? And so we go through that process for each of the central atoms. And so we end up with a nitrogen that's a trigonal pyramid. We end up with a carbon that is a tetrahedron. We end up with another carbon that's a trigonal planar. And an oxygen that is a bent geometry, right? And so that's how we're going to approach molecules that have more than one central atom. Okay, so now let's jump into polarity. So if we remember last chapter, we talked about polar bonds and how we used electronegativity as sort of the primary way that we can determine whether a bond is polar. Well, how do we expand that to a molecule and determine if a molecule is polar? Well, a polar bond is part of that structure. So let's look at what we mean here. Well, let's start with a simple diatomic here. So in a simple 2-atom molecule, we look at the bond, and if that bond is polar, so remember we're going to use what we call the difference in electronegativity here. And we're going to assess the difference in electronegativity, and if it's, above 0.4, this bond is polar. Now, since there's only one bond, this is a polar bond, and therefore it is a polar molecule, right? Because that's the only bond, there's no other factors involved. So if we have a simple diatomic, if the bond is polar, the molecule is polar. Remember, what that means, right, is if we have a polar bond, we end up with a dipole. Now, in a molecule, what we're looking for is the overall dipole of the molecule. So we're going to look at the bonds and look at their dipoles and look at how all those dipoles combine to give us an overall dipole for the molecule, or what we call a net dipole moment for the molecule. Now again, very simple. If you have just 2 atoms, right, you look at the bond. If it's polar, well, then the molecule's polar. But what if we have more than 2 atoms? Well, let's look at a couple examples here. So let's look at CO2 here. So if you remember from Lewis structure, right, the best Lewis structure here we have for CO2 is 2 double bonds. So we have 2 identical CO bonds. Now, individually, right, each of those bonds is polar, right? Okay, so we have some polar bonds. That's good. Now, we have to have polar bonds in order for there to be a polar molecule. But if we look at here, if we look at the dipoles, the dipole moments of each of these bonds, what we see is they're going to be exactly the same. And because of the arrangement here, right, this is a linear structure. So these oxygens are exactly opposite each other, 180 degrees. these dipoles are going to cancel each other out because they are exactly the same size and pointing in exactly opposite directions. Now, for those of you who have maybe worked with something called vectors, this is going to seem a lot more familiar, right? We're doing sort of a simple version of vector addition, right? Where these dipoles have a direction, right, toward the atom that's more electronegative, and they have a magnitude, right? We can think of the magnitude as the difference in electronegativity or the dipole moment, but they have a magnitude. And if that magnitude, if those dipoles cancel each other out, or those vectors cancel, then the overall dipole is 0, right? So CO2 is nonpolar because there's no net dipole, right? The polar bonds cancel each other out. Now, what if we look at something like water, right? Also has 3 atoms, but if we go back and look at the geometry of water, remember, water looks like this, has the 2 lone pairs, right? So it's a bent geometry. So if I draw this out and I draw the dipoles, notice they're pointing toward the oxygen, and of course they're equal. But notice they are not pointing exactly in opposite directions, right? They are pointing sort of left and right, but they're both pointing generally up. And so therefore, or toward the oxygen, if you will, in the way this is drawn. And so there's a general upward point here. And so we're not going to cancel out, right? We're going to have an overall dipole that is pointing up here. So we end up with a positive side here and a negative side here. So again, it's all a matter of whether these dipoles here and here will cancel each other out. So here we have polar bonds, but the dipoles don't cancel, and so we have an overall molecular dipole, and so we have a polar molecule. So CO2, nonpolar, water, polar. And again, so what do you think? The geometry becomes important here, right? We have linear versus bent. The linear molecule is nonpolar, the bent molecule is polar. So how do we go about predicting the polarity? Well, first, of course, we have to start with the Lewis structure and use VSEPR to give us the geometry, right? So we need the geometry. We have to determine whether it has polar bonds, right? So again, we're going to use difference in electronegativity to do that. Now, of course, if there's no polar bonds, then the molecule is automatically nonpolar and we can sort of stop at that point. But if we do have polar bonds, then we have to determine if the polar bonds or the dipoles add together to give a net dipole or if they cancel each other out. So we need to assess the symmetry of the dipole, or another way to think about that is we have to look at the symmetry of the molecule. And that's going to come down to the geometry. So we're going to need to look at the geometry and see if that's a symmetric geometry or a non-symmetric geometry. Okay, so let's see how that works. Let's look at some examples here. So I'm not going to go through all of this in excruciating detail, but this is sort of simple vector addition. So, for example, if you have 2 vectors pointing in the same direction, even if they're equal, right, of course they're not going to cancel out because they're pointing in the same direction, they're going to add together. If vectors are pointing in the opposite direction, they will cancel out, but if they're not the same magnitude, then you'll end up with a net dipole and a polar molecule. So, for example, if you had a linear molecule, but the 2 sides were unequal, or they weren't the same atom, then you could have a polar molecule. So it's not just the shape, right? It's the atoms that are involved, right? So the shape can be symmetrical, But if the atoms are different, then the molecule is still unsymmetric. So we have to look at both the shape and what atoms are present. Now, of course, if those atoms are the same, so the vectors are the same, the dipoles are the same, and they're pointing in opposite directions, then they're going to cancel out, and you end up with no dipole, and you end up with a nonpolar. Okay, so linear is all great, right? But what if they're pointing at angles like we saw in that bent geometry? Well, the idea is when you have an angled vector, if you want to, you can break it into horizontal and vertical parts. So if we kind of look at that bent geometry here of water, we saw that, right, we had the dipoles were like this. Now, each of these dipoles has a vertical component and a horizontal component. A horizontal component and a vertical component. Now, because these vectors are the same, right, and the angles are the same, right, the horizontal components and the vertical components are the same. Notice that the two horizontal components actually do cancel each other out, right? They're equal opposite directions. But the vertical components are additive, right? They're pointing in the same direction, so they don't cancel. So this is why we said we end up with an overall dipole pointing generally up, like what we saw. So this is the idea of when we add angles of the vector, we can imagine or think of them with horizontal and vertical parts, and we can see what cancels. All right, so let's think about the geometries. So of course, if we assume that all of the, if we have our base geometries and all of the atoms are the same, right? We have just bonds and all the atoms are the same. A linear structure is symmetrical, right? So a linear structure will be nonpolar. A trigonal planar structure will be nonpolar, right? The dipoles will cancel. A tetrahedron, again, symmetrical, will be nonpolar, right? So assuming that all the four atoms are the same. And this goes for any of the basic geometries. We can expand that to trigonal bipyramidal, octahedral, right? If they're all bonds and all the atoms are the same and all this, that's going to be a symmetric structure and all the dipoles are going to cancel out. Now, if we take any of these and we switch these up, so we change, say, two of these are the same, but one of them is different here. So let's say we have H, and this is a Cl. Right? Now they're not the same, so they don't cancel out anymore. Now it's non-symmetric. So while trigonal planar or tetrahedron or any of these are symmetric shapes, if all of the dipoles are not equal, then it's still a non-symmetric, and it's going to end up being polar. Now, what if we have a geometry that has lone pairs, like bent or trigonal pyramid? Well, any geometry with lone pairs will be non-symmetric, meaning if it has polar bonds, it will be polar, right? So you can't have, say, a trigonal bipyramidal that has polar bonds be nonpolar, right? Because the dipoles in any of these non-symmetric structures with lone pairs are never going to cancel out. So if you have a polar bond and you have a structure that has lone pairs, it will be polar always. So that's a good thing to keep in mind as you're looking at the structure. So if you see something that's, say, square pyramidal, right, and it has polar bonds, then automatically you can say it's polar, right, if it has a lone pair. Okay, so this is something that takes a little practice, right? We have to work with this to get used to doing this kind of thing. Okay, so we're going to leave this for a second, and we're going to talk about a related topic with polarity, but a more sort of actual example here of where polarity comes into place. And that is how polarity of molecules affects their solubility in water. Now, you might remember that we've talked about solubility a little bit, and I'm sure you have experience with, say oil and water being not soluble with each other, but things like sugar and salt being very soluble in water. And this comes down to a premise that like dissolves like. So what that means is that polar molecules are attracted to other polar molecules. And so if I have a polar, what we call solvent in water, it will be easy to dissolve other polar materials in that water. So because water is polar, other polar molecules will dissolve well. And that would include ionic compounds, because if we think about it, right, ionic is just extreme polarity, right? So we're not worried about dipoles, right? We have ions, right? So ionic compounds are very polar. But on the other hand, if we have non-polar molecules, they do not dissolve very well in a polar material like water. Now, why is that? Well, let's look at maybe why polar molecules dissolve so well in each other. Well, remember, polar molecules have dipoles, right? They have what we just talked about. They have an overall molecular dipole. Well, that means we have a positive side of the molecule and a negative side of the molecule. Now, the positive side of the molecule is going to be attracted to the negative side in a different, say, water molecule here. And that would be the case for any polar molecule. So if this were another polar molecule combining with water, like alcohol, like ethanol, then they're going to be able to have these attractions because they both have dipoles. Now, we'll talk about what this connection is here, right? This attraction is a type of what we'll talk about in the next chapter as an intermolecular force. And it's what holds molecules together. Now, I'm not going to go too much into it now. We'll get into detail about it next chapter. Now, but why do nonpolar molecules do this? Well, it turns out that nonpolar molecules can't make the same kinds of attractions as other polar molecules can, because they don't have a dipole, they don't have a positive and a negative part. They can't be attracted in the same way to other polar molecules. So oil molecules, which don't have these positive and negative sides, don't have really a good way to be attracted to water. They can't form these same type of intermolecular forces. So one way to think about this is, right, you've probably maybe experienced this where they separate, but if you take, say, oil and vinegar and you shake it up to try to make an oil and vinegar dressing, you can kind of get it to mix. But if you let it sit there long enough, it'll separate. And this is kind of like if you were to imagine taking magnetic marbles and mixing them with normal marbles, right? You can mix them all up, but if you sort of just even keep sort of jostling them, eventually the magnetic ones are going to be attracted to one another, because magnets are, and they're going to squeeze out the non-magnetic marbles at the same time. So to form these attractions, they kind of squeeze or push the non-polar, if you will, molecules out of the way. And that's what happens here. Eventually, right, the oil just starts to sort of separate and float to the top and congregate together. The water is forming these types of interactions and squeezing out the non-polar molecules that can't do that. Well, you might ask, well then how do we use, water to remove oils, like when we wash dishes or wash clothes or wash our hair. Right? Well, notice when you do that, you don't just use water to wash your hair. You use a soap. So soaps are special types of molecules that have both polar sections of the molecule, what we typically call a polar head, and non-polar sections of the molecule, which we typically call a non-polar tail. And these act, if you will, like bridges, right? Where the polar head is attracted to the water, the non-polar tail is attracted to the oil, and the soap molecules hold the two things together. So they allow the oil to, if you will, stick or stay close to the water, connected to the water, and that allows, with the aid of the soap, the water to, in essence, dissolve the oil or carry it away down the drain without it sort of sticking to everything, because the soap molecules keep those things connected. So the soap acts as a bridge that allows that polar molecule to attach, if you will, to the non-polar molecule and carry it away. So that's how we can use soap. It makes it possible to use water, a very polar material, to clean non-polar messes like oils and greases. Okay, I want to close off this section by doing a couple of examples of assigning polarity. So let's do first, we'll do CF4. So remember, the first thing you have to do is do the Lewis structure in geometry. So this first example I'm going to take all the way through, and then maybe I'll do another one, but we'll kind of start off, with what we already know. But I want you to see the process here. So CF4. So remember from chapter 10, draw the Lewis structure. We're going to count up the electrons. So we have 4 from carbon plus 7 from the fluorines. So 4 times 7 gives me a total of 32 electrons. So we're going to draw the skeletal structure, right? Putting carbon, the lowest electronegativity, in the middle. Well, put the fluorines around here. And we'll connect each of these by a single bond. And that's going to use 8 electrons, leaving me with 24. Now, we're going to start putting in lone pairs to satisfy octets. We see that each of the fluorines needs 6 more. So we need 6, 12, 18, 24, which we have. So we'll go ahead and do that. So 24. So we've used all of our electrons. We check to see, does carbon have an octet? Yes, it does. So everything has an octet. So we have our Lewis structure here. Now, geometry. So if we think about our geometry, we have 4 electron groups, right? 1, 2, 3, 4. So we have 4 electron groups. Now, if we have 4 electron groups, that tells me that I have tetrahedral base geometry, we call electron geometry. Now, what about the molecular geometry? Well, to determine the molecular geometry, we have to look to see if there's lone pairs. So in this case, our four electron groups are all bonds. So we have no lone pairs. So that means our molecular geometry is equal to our electron geometry. So our molecular geometry equals tetrahedral. Okay. So if we have tetrahedral, now we can start to look at the polarity. Well, the first question we have to ask ourselves is are there polar bonds? So let's assess the polarity. So polar bonds. So we have to do the difference in electronegativity. So the delta En here equals 4 for fluorine minus 2.5 for carbon equals a difference of 1.5. So yes, so clearly we have polar bonds. Now what about the shape? So a tetrahedral geometry is symmetrical, right? Because it's a base geometry, no lone pairs, so it's default symmetric. Then we have to say, are all the groups are the same? So yes, we have all four bonds are the same in our symmetric geometry. So we have polar bonds, but we have a symmetric shape. So the result here is we have a non-polar molecule because all of the dipoles in our tetrahedron would cancel each other out because they're all the same. Okay, so this is a non-polar structure. Okay, let's finish out with one more example. So we're going to do PCl3 here. So I've already drawn the Lewis structure, right? We did this in class when we were doing chapter 10, and this is one of the structures that we drew in class for our Lewis structures. And so it's going to look like this. So we're going to see it has 4 electron groups, right? 1, 2, 3, 4. So that gives it a tetrahedral electron geometry. Now, we ask ourselves about the molecular geometry. Well, we need to see, does it have lone pairs? And so, yes, right? We have one lone pair. So if we have a tetrahedral electrogeometry with one lone pair, that means the molecular geometry equals trigonal pyramidal. So that's my molecular geometry. So now let's look at the polarity. First question, of course, is polar bonds. So the difference in electronegativity, right, equals, let's see if we consult our table, we have chlorine that has a value of 3, phosphorus is 2.1, so we got a difference of 0.9, so the answer is yes, right, we have polar bonds. What about the symmetry? Well, if we look at here, right, well, trigonal pyramidal geometry, because it has a lone pair, is by definition non-symmetrical, right? Even if all of these atoms are the same, the fact that we have a lone pair means that the dipoles will never cancel out. And so, because we have the lone pairs, this is automatically non-symmetrical. So we have polar bonds, we have non-symmetric structure, which means the dipoles won't cancel. So that means we have a polar molecule, right? Because we've satisfied both criteria. We have polar bonds we have a non-symmetric structure. Okay, so that's a little bit about assigning polarity to molecules. Next time, we'll come back, we'll look at theories beyond Lewis structures.